this field because it is really exciting at the moment and there's a lot of innovation. I'm going to put in the chat a link to the slides, just in case somebody wants to follow along on their own rather than follow me as I'm going along. So the paper is a fairly long paper. It's got about 50 pages of genuine text and about 70 pages worth of references. And its main strength is really, it covers a huge surface area, obviously, but it does give references to a lot of open source projects. Gives links to GitHub and kind of describes and summarizes most of the areas that reinforcement learning is being used in the agentic kind of AI kind of sphere. So if I begin. So in terms of, I'm going to do this via this presentation because it's a very long paper and I'm not going to go through each individual kind of section of it. So in terms of the overall presentation, I'm going to give a very brief introduction to reinforcement learning, which is RL. There's going to be no maths in this particular talk, although the field is fairly mathematical because it involves kind of like stochastic models and is fairly well developed. But we're going to keep it at kind of slightly more application level because I'm a developer. I like to actually build things. I'm not a theorist. So that's how I learn. So a little bit about what is Agentic RL in this context. What are we talking about? And then what the paper's actually done is they've broken down all the core features that an agent would need and how RL is being applied to that kind of particular sort of aspect. So here they've got planning, tool use, memory, reasoning, perception, self-improvement. And once they've done the kind of like the core features, they've given like within each application area, how that applies to search, coding, maths, GUI. It isn't exactly one-to-one because different systems use different kind of like parts of this, and some of that is evolving. But yeah, it is nice that they've got the applications, and again, they put references to a lot of systems in the different application areas as well. So I should say that this paper is really about open source. It doesn't really spend a lot of time on the closed source systems because they're not very well documented, and there's a lot of like trade secrets, so we don't really know what's going on. And then a short conclusion and then some resources. So any of you who are not really reinforcement learning kind of like people and you want to really learn about reinforcement learning and maybe kind of really get up to scratch on it, I'll put some resources on there, and they are really excellent. So great. So we carry on. So first of all, what is reinforcement learning? So typically we have an environment, and it's a complex environment. So a bit of, this particular game, which is, I think, World of Warcraft. So we have an environment that we want to do something in, and we also have an agent. And the purpose of the agent is to perform some kind of action in the environment, or a set of actions, because it's trying to achieve some objective or other. So an agent performs an action, and then the environment gives it back, sort of evolves to another state because you've actually done some action on the environment. And you actually get the reward from the environment. And typically, the state of the environment is really too complex for the agent to kind of handle. So what we actually get is an observation. So what the agent gets is a function of the state. It's usually a very partial function, because as I say, the state that we're normally dealing with is simply too complex for an agent to handle. And the most critical bit here is that we do get a reward. So the idea is we've got some kind of idea if the action was good or not. Now, for most systems that we build, the reward is what's called sparse, which means that on any particular action, you might not get any reward because you haven't achieved your objective. You've only gone partial of the way through. An example is something like chess, where you may do a lot of moves, and actually only when you won, drawn, or lost do you get a reward. And you don't know whether any particular action was good or bad. And again, that has advantages and disadvantages because, as you can imagine, for a game of chess, this could go on for quite a long time with a lot of moves. And if the only signal you're getting is at the end, hey, you won or you lost, that's quite a tricky problem to solve. And in some sense, that is the reinforcement learning problem. Okay, so in a little bit more detail, what are the challenges in this field? And there's quite a few. A few years ago, reinforcement learning was maybe regarded as being not really fit for purpose because it was so difficult to use. But actually, I think that's changing now. We have better algorithms, more data, and systems that are practical, which are actually being used, which we're trained with this. So in no particular order, right at the top, we have sample efficiency. So machine learning, we need a lot of data. And typically, the more data, more higher quality data we have, the better system we can build. And one of the problems can be in reinforcement learning is that some problem domains, we get a lot of data. For example, if it's gaming or coding, we can get a lot of data. But in a lot of other environments, in many environments, it's just really difficult to get good quality data. For instance, robotics. If you want really practical built robotic systems, you're going to have to get really good quality real life data. And again, that's a real challenge. Another major issue, a bit like the chess problem, where you've done a lot of different moves and finally you've got a win or a loss. You don't know which particular move actually really helped. And so that's called the credit assignment problem. It's like you've done a huge number of actions. How do you assign like a reward or some kind of saying this action was better than another action? Another issue is exploration versus exploitation. So most of the problems we deal with are really huge. And what we would like to be able to do is the agent to explore that environment and kind of build up a policy. And a policy means kind of like what it's going to do. But we don't want to do that forever. We do want to be able to then take that training and actually exploit it in some way to actually solve the problem. So there's always this kind of balance we have to strike between exploration, try and learn as much as possible, but actually then exploiting you to actually solve some sort of problem that you're actually genuinely interested in solving. Again, moving on to the next one, another major problem is reward engineering. It's actually really difficult to design good rewards. And rewards can have a massive impact because they actually govern how the agent's going to behave in this environment. And there's always a risk of what's referred to as reward hacking, where the reward you design, which you thought was going to do what you wanted it to do to get the agent to behave in a certain way, but it's actually hackable, so that the agent shortcuts to get the reward without actually solving the problem. And this is, and so you always have to be aware, if your agent's doing really well, is it really solving the problem, or has it found like a shortcut to get the reward without actually doing anything, or doing anything really useful? Another major issue is stability and convergence. So reinforcement learning has traditionally had a very bad reputation in that it's really difficult to train. Because rewards are very sparse, where we're saying we do a lot of actions, we don't know whether they're good or not. Eventually, we may get a reward. It just means the training is very unstable. Small changes in any of the hyperparameters can just destroy particular performance that you had previously. And actually, this is one of the areas where people have invested a lot of effort and had some success in making training kind of more stable. So DeepSeek, one of their innovations was that they actually introduced a new algorithm for actually doing a new algorithm for the loss function in their reinforcement learning, and it was performed better and was cheaper. So that's one of the reasons they were able to build their system cheaper than previously. Another major problem is partial observability, which is the world is really complicated. Your agent can't possibly have a real, solid belief about what the world is really about, what the current state of the world is. So it has to be grossly simplified, and that obviously has side effect that you don't really know what the state of the world is, but you have made some assumptions about it. And finally, reinforcement learning unfortunately has this behavior where it really overfits on the training environment. So if you depending on your training data, you can find that it works perfectly in training and then just does not work as well in real life. So with all these problems, we still can get decent systems, and they're getting better and better all the time. But these are kind of like the problem that everybody kind of tackles on each of their domains sort of every day. So moving on. So in the context of this paper, what is Agentic RL? So reinforcement learning has been used in training LLMs for quite a while. Basically, we tend to do that right at the end. So our LLMs normally get trained, first of all, with just massive amounts of internet data where they just predict the next word. And the output of that is gibberish. And then they're fine-tuned on some preference data, which is where you actually give example prompts and responses, and they start to behave a little bit better. And finally, we use reinforcement learning with human feedback, which is where humans are actually picking, this was a better response than that one. And that final training is what ChatGPT used to really get really good, good performance as a chatbot. So that's traditional reinforcement learning. What we're talking about here is where the LLM is kind of like part of a bigger sequential decision process. So the LLM is doing something, some actions are being performed, some tools are doing something, and then that's being fed back into the LLM, that's doing something more, and then iteratively until the problem is solved. So in this particular case, the policy of the agent, that what it's choosing to do, is being embedded in this kind of long sequence of steps, and the LLM is integrated into them as kind of like the thing that puts in the intelligence into it. Okay, so if we move on. So the first core feature that we're interested in kind of getting working with the reinforcement learning is planning. And the paper sort of splits this into two different categories of planning. So one is where the LLM is kind of working, and what it's doing is you're giving it a prompt, it generates some potential actions to perform, and then you're actually taking those actions and then training an agent to kind of pick, kind of decide what the reward for each of those actions is. And then, so you're training, so the LLM is not being trained, but the reinforcement learning is. So the actions that the LLM chose are what's training the agent. And then eventually that training, they use Monte Carlo tree search to actually navigate that in the final system. So here the LLM is not changing, it's the agent, which we are training separately, which is changing. And there's a couple of papers here which they as exemplars of that kind of approach. So the alternative to that is where the LLM is actually part of the actual planning system. So it's got actually the agent is integrated into the LLM. And RL feedback is used to train the LLM. So the LLM weights themselves are changing based on the RL feedback. And so this is a bit like the reinforcement learning from human feedback, which ChatGPT used, but on steroids. You're just doing it over a much more complicated process, and you're trying to get the LLM to kind of follow that, to try and complete that process. And there's a couple of systems that they mentioned here, which kind of exemplify this approach to that. Okay. So as I say, I'm whizzing through a few different use cases. I'm not going to go into depth in each one because there's just a lot of use cases. Tool use is another major use that we want to make use of in agents. And here, this is kind of like a timeline. So the original systems were kind of this kind of approach on the left. And then we've evolved into the current phase that we're in now is the tool integrated RL, which is in the middle. And kind of the future is what we're looking at the end. And there's a couple of experimental systems there, but they're not really the majority of systems that we have. So if we look at the very first ones, so you basically give some few shot examples to the system, and you're kind of, what you're trying to achieve is a cohort action observation type output from the LLM. So it's a bit like the thinking mode. Typically, these are supervised fine-tuning kind of models. And the issue here is that you've got like this data set on which you're training the LLM in terms of how it's going to do the reasoning and what actions it has available. So this is not dynamic. This is kind of static data that you've kind of like fed into the LLM. An alternative is where the tool is integrated into the LLM. Again, now we're training the LLM, but the tool is part of that, and the feedback the tool gives is part of the training of the LLM. So a bit like the previous one here. Now it's the LLM itself that's changing, but not just through a supervised fine tuning. You can call APIs, you can run tools, and the output of that is what's giving you that. And there's a lot of systems in this kind of category: OpenAI Deep Research, Kimi, Zippo, and an interesting paper in this one is the Tool RL, reward is all tool learning needs. So that's like trying to get LLMs to use tools. So the future is much more complicated environments and more steps in the actual that the agent has to follow. And the issue here is always, we want to do a lot more complicated to it, instead of being, very limited sort of tool use, a much more kind of like complex environment. So as with all of these, the future will be more complex, more complicated decisions, more complicated environments, longer steps, interdependent steps that the LLM is following. And there's a couple of promising papers they mentioned: grouping, group policy, and spiral, stepwise progress attribution. So this is where people are kind of moving towards, rather than sort of the simpler tool, the use that we've had in the past, or the way the current system is working, but again, towards more complexity. Another feature that current LLMs tend to not have is any memory. So, and the core problem here is, what do I store? When do I retrieve it? And how do I forget it? Traditionally, there is one particular approach, which is to use the memory that the LLM has in a RAG data store, which is a retrieval augmented generation style memory. And essentially, an example system they were mentioned in this kind of category is memory R1. And what this guy has is it's got two kind of features in it. One is where the LLM has access to these additional instructions: add, update, delete, and no op, which it's able to use to be able to access the memory in the RAG database. And during training, obviously, it's learning when to use add, update, delete. And then finally, and they've also, and then a second phase is where, end to end, it is the first bit is what instructions to use to add, update, delete. And then the second bit is an answer agent, which actually retrieves the data from that data store, filters it, reasons over it, summarizes it. And this combination, which is used in this RAG style, has been reasonably successful on Locomo, which is a long context memory benchmark. But as I said, that's where the actual memory itself is in a data store. An alternative approach to memory is where the memory is actually kind of inside the context. So one particular approach is where you've got like so let's say you've given the LLM a prompt. That's usually encoded as tokens and then processed chunk by chunk. And so in this approach, what they've done is they take so your prompt, you get that into a chunk, but then an additional chunk is appended to it, which is the memory. And memory is what the LLM keeps. So the memory is now tokens, and this kind of like slightly extended chunk is then given to the LLM, and its output is your normal output chunk, but also the new memory, which is basically it's updating. So the last memory it had is being updated with the new chunk memory. So here we're storing the memory as essentially tokens in the context of the LLM. There's no separate external kind of like memory for that. So that's called explicit tokens. An alternative approach is called implicit tokens, and that's where the memory is actually stores additional parameters in the LLM. And I haven't fully sort of looked into how this is working, but essentially you're training these additional memory-specific parameters. And the LLM is learning how to use memory operations on those parameters. And then during inference, it actually uses those parameters. And that's implicit tokens because they're within the LLM's weights themselves rather than external to it. Okay.
If I may?
Sorry.
I have a quick question. A big part of reinforcement learning is the representation learning itself, right? Where how do I take my data and essentially put it into a vector that I can put into an RAG database or so. How would one deal with the problem that as one learns the RAG representation itself shifts about?
So reinforcement learning itself is not really a bad representation of data. So if you remember in the original kind of like description of our reinforcement learning, well, we have an agent, it performs an action, and the action does something to some system, which is the environment, and the environment gives you back the next state of that environment and a reward.
Yeah.
So the agent itself, and obviously it has this state, but its state is really just like a bookkeeper of where I think I am now. It's not really necessarily keeping kind of memory. It's the environment that's keeping the memory. It's, the environment knows what it states in. The agent kind of has a little bit of bookkeeping to itself to just kind of map, okay, I'm in this kind of state now. What action should I take
But isn't
to get a better reward?
the issue,
and you're training that end to end. So
yeah, but because the number of states tends to be very, very, very large, right? So you can't obviously have a lookup state to action. So typically what happens at some point, you have some form of representation of that state that is higher level. Like if you have a picture, does a picture show a cat or so? And if it shows a cat, you do something. Wouldn't, and especially when it's a RAG database, right? So RAG almost by definition stores a compressed view of your state or internal position of where you are. Wouldn't that be a problem, particularly in reinforcement learning, where the way you look, you learn essentially new concepts as you do your reinforcement learning, but those concepts might be completely meaningless in the old language with which you stored your past data.
I think I know what you're saying, but I'm not quite sure I would think about it that way. So if we imagine we have an LLM, unless it's one of these implicit token ones, which has additional parameters and it's got some operations it can do on those parameters. So the agent doesn't know about these operations. It doesn't know it can do. It doesn't even know there's a memory, to be honest. So the agent, all it knows is, okay, I have this task to perform, and at each stage I can take some action, which is the input to the LLM. It's not so it's some prompt, it's some action, and then the LLM kind of does its thing, and then outputs a state and a reward. Or outputs a state, which there's a reward function which we can use to compute whether it's a good action response or not. So the LLM is a black box. The memory it has, how it works, what it does, we don't know what that is. All we know is that we sent some action into it. It did some stuff. It told us, some result, and then we can get a reward of how good that result was. Yeah. And all the agent's doing through backpropagation is to say, hey, this reward was good or bad, and the loss function of the LLM, which we're backpropagating, has got this notion of, okay, I took all these actions, were they good, were they not bad, which one's better, which one's worse. So the idea is the backpropagation is really backpropagating the end result. How you actually work out what to store and how to store it is up to the LLM and what operations it has. So I kind of know what you're saying. So the LLM itself needs to know, how do I store memories? How do I retrieve them? What can I do with them? But the agent and the reinforcement learning doesn't care, because, obviously having richer operations within the LLM might help the overall training.
Yeah.
But that's not the agent's concern. It's the LLM designer's concern to say, hey, I need some more operations. I need a better database. I need to do something.
So we sort of define the problem around it, that whatever memory we need, we just we assume it's there.
Yeah, so I can kind of see what you're saying, that representation obviously matters. Some representations are grossly inefficient and don't capture the information. Some representations are better. So the LLM designer has got to kind of design, like, for instance, what memory operations it allows, what query operations it allows. But the overall reinforcement learning kind of aspect of it is really this kind of loop of, did I get a good reward or not? And that's what you backpropagate through the LLM. Yeah. And it's the LLM to decide what operations it has or not, and then through the backpropagation. And because the loss function is differentiable, just like normal sort of like machine learning, it can do that.
So I might have lost it. So do you still update the LLM as you reinforcement learn?
Or, yes. So in this case, the implicit tokens, yes.
Yeah.
Because the I mean, here we're in the training phase, right?
Yep.
So the agent has kind of decided on an action. It doesn't know whether it's good or not. The LLM does something, generates some kind of output, and then we get a reward from that, which is our loss function, let's say.
Well,
and then we back-propagate that loss function through the LLM and update its weights. This is what, this is in some sense the power of the reinforcement learning, is to say, hey, I've got this interesting loss function based on the action that was taken and the reward I got. Can I back-propagate that through the LLM to get it, to learn, a better behavior?
But the LLM wouldn't output the action itself, right? It would output some representation of an action, maybe, or recommendation, but the agent would still have to assign the value to an action, right? I mean, when you train the agent.
I mean, the LLM would typically output a range of actions with probabilities.
Mm-hmm.
So it wouldn't be like a single action, but it would output what the agent. Oh, sorry. No, you're quite right. What the LLM is outputting is kind of like the reward of, or like it's going to generate something which there'll be let's say a separate system which will evaluate how good it was, right?
Yeah.
And then the reinforcement learning policy update, which is a separate thing, would be, okay, was this a good or not?
Yeah. Yeah. Exactly. So the agent wouldn't technically have to know that there is necessarily a LLM involved, right? He could just take the output of the LLM as its state, whatever that is. No.
And for it is sort of a black box.
Yeah.
Because all it's really interested in is rewards. Really, it doesn't really know. Actions, the rewards is what it's mainly interested in.
Because if you say the outputs of the LLM are the rewards or expected rewards, then it is the LLM itself that has to update, right? Because that's the
no. So the output of the LLM is the agent's done some sort of action, and the output of the LLM is the next state and reward. But like it's not exactly a reward, because usually we have a separate kind of reward kind of estimation function. But it's kind of something that can get me what the reward would be for that output of the LLM. Yeah, there would have to be a score whether this was a good output or a bad output.
But of course, the whole point is learning what that is, right? Because a priori we don't know.
Typically, as I say, for reinforcement learning, it's really whether it was good reward or bad reward, and then obviously, the better the reward, whatever once it was. Because typically the way RL algorithms are kind of like conceptually imagined is that the system is kind of like a black box. So usually, let's say imagine that you were playing the game, right? Like let's say World of Warcraft or something like that, right? Yep. And then you made some sort of a little trip through the maze or whatever, and got a bit of health. So the agent doesn't necessarily need to know that the world is this way or that way. All it needs to know is that action I took gave me some health back. Yeah. But like it doesn't need to know everything about like that environment.
Yeah, but that's why what I'm saying, that the agent doesn't receive the world through the input of an LLM, and does the agent only see the output of the LLM? Or is the LLM sort of part of the agent that is actually making the decision, or at least the evaluation of which action is more likely to be valuable than the other?
Oh, okay, I think I understand what you're saying. The LLM is what's kind of outputting the action that should be taken.
Okay.
Okay. Sorry about that confusion, because I think I misunderstood what you were saying. Yeah, so the future is really currently, the memory I've just described is very simple. So it's a much more sophisticated memory, that has richer relational, temporal, or hierarchical kind of aspects to it. And manipulating this dynamically in terms of the memory. And there's a couple of systems that I mentioned there, ZEP, AMM, and G memory, which do different types of memory. So carry on. So another core feature we quite like is self-improvement of the agent. You know, what we've already got, how can we iteratively improve the agent? And there's a couple of different approaches to that. One is purely during inference, and we kind of have so it's if or else, so that we get like a couple of alternatives from the LLM, or maybe we got some confidence intervals, and then you know, a lot of these thinking type models, they have within the inference themselves more reflection, kind of critiquing of whatever they've been doing. So this is where there's no training. It's part of the inference that's actually coming out, that it's within that loop that it's actually kind of self-reflecting and trying to get an improvement on that. Sometimes uses some external guidance, so there's some tool that it can check whether what is just generated is correct, but typically it doesn't involve anything kind of within the LLM itself. And an alternative is where the agent is constantly kind of asking self, no self, which is like, do I need to look this up, or can I figure it out myself? So have I got some additional knowledge, or do I need to call an external tool to get this additional information? Another one is where it kind of critiques itself. It's like, did I get this correct? How can I fix this kind of error? So it's a little bit like the inference case, but this is really where you can call out tools, where you can kind of just really kind of like self-reflect on what it was doing. And ideally, obviously, we'd quite like it to be iterative, so they continuously kind of is in that loop. And this has had quite a long history. So AlphaZero, which was trained on self-play, is a classic example of kind of like self-training. And there's a few different approaches. Execution guided curriculum, where the LLM creates problems, solves them, and then goes and checks whether or not solution was correct as part of the kind of like the training. And then there's collective bootstrapping, which is like a system where it expands its knowledge base of tools that it knows and how to use. So it's quite an interesting system. And the future is kind of meta evolution, where it's just the RL is applied at a higher level to kind of like encourage more of the reflection and adaptation. So it's a little bit ill-defined in terms of what meta evolution may mean, but it's just really, the alternative is hard coding basically. So we're trying to move away from really hard coding this kind of like thinking aspect, and trying to get RL to kind of do it at a slightly higher level. How am I doing for that? Okay. Reasoning, another core feature. So it ideally like systems that have got both system 1 and system 2 type reasoning. We quite like some reasoning that which is fast, heuristic, minimum number of steps, and some reasoning which is slow, deliberate, structured. So fast reasoning is how most LLMs work at the moment, which is obviously the training, which is next token prediction. Unfortunately, fast reasoning, as with most heuristics, there can be factor errors, biases, hallucinations. And there are some slightly more kind of like methods which we can use to kind of improve that. Confidence estimation methods to see how confident the LLM is about a particular response. So this is kind of system 1, which we currently kind of have. And system 2 is where it produces intermediate reasoning traces, and we have got systems like this now. So DeepSeek R1, OpenAI, and models can use self-play, so they generate a problem and solve it, and use that to guide it. And one of the major issues is basically it's just slow, and there's really prone to overthinking and getting into a loop of overthinking. And the future in terms of reasoning, really getting more towards multimodal type data grounding, so that the LLMs can actually query back on data that they are certain of. For instance, if there's an image and they need to reason about that, to be able to go back and query parts of the image. Generating sketches as part of the of your context as your reasoning. Images, again, we have systems now that are starting to do this, which is part of their, and then audio, question answering. So really, more multimodal is the future in terms of reasoning. So I'm only going to cover a couple of these search and information retrieval ones, because there's quite a few, and each one has got its own systems. But overall, the kind of approach is kind of fairly similar, although particular details are different. So right at the first and probably the most common is search. So LLMs are being used a lot in search and information retrieval. So ideally, what we would like is a search that works, that is multi-step process, that involves finding information, doing in-depth analysis, synthesizing the insights, and creating reports. So we would ideally like all of these to be happening as part of this kind of like agentic task. So search from the internet, obviously we do have systems that already do this. RL is usually used to optimize the query that the search engine is going to, the LLM is going to use to do the search. And there's a couple of systems they mentioned, R1 Search and WebDance, that do that. The major issue is that the quality of the documents they can get back may not be fantastic, because obviously we're relying on an external search engine. And API costs are very high, so that is an issue in terms of training, because we do need to acquire a lot of data. So because of those two, really only the very big companies can probably afford to try and do this. Another alternative which people are exploring is to actually use the LLM itself as a knowledge base. So either a search engine which is distilled from the LLM, or the LLM kind of uses its own knowledge as search. And the main bits of this are that obviously scalability is not an issue. There's plenty of data and stability. Closed source methods in the information retrieval. BrowseComp, which is a new benchmark from OpenAI. This is quite an interesting benchmark, because what it tests is an information retrieval request that requires multiple sources, very hard to find information, synthesis. And they've released this as open source, but it was only done earlier on this year. So we only have OpenAI's deep research as what its score is, which is 51.5. Other systems hopefully will start to release their own systems on this benchmark, and I think this would be a fantastic kind of research to really push this forward. So the future is more advanced tool integration, memory modules, so that you've got and interactive iterative researches, so that you can, once you're in a loop, you can iteratively improve the results. So yeah, more complex, longer running tasks. Code generation. So this is really the ideal test for LLM agents and what they're capable of, because of the huge advantages that we have in terms of excellent reward signals. We know whether the code compiles. We have unit tests whether it does the right thing. We can get runtime traces. So much really good information in terms of rewards to be able to drive the reinforcement learning in these kind of environments. So historically, RL in this particular area has been used in single code generation. So typically, you will give a prompt, which would be generate a function with a certain spec, or typically put in like a doc string and a description of what you want. And as with all of these, the major, so actually for a lot of these kind of like actual applications, there's two main categories of approaches. One is outcome reward RL, which is the whole system end to end, where you're giving a reward if the system achieved the correct result at the end. Now, the problem with that is the sparsity and the credit assignment, because you might have done a lot of different steps in the middle to achieve that final result, but then how do you kind of like get the right amount of credit into the right bit? The idea would be if you would get outcome reward working properly, because that's really what we would want. We would want, okay, it solved the problem and you found some amazing way to do it. We didn't have to say, hey, try this, and this is better than that. The alternative is process reward, where we break down the particular task that we want into different steps. and at each step, it follows a certain process, and then we give it a reward as to how good or bad it was. Obviously, this is guiding the search a lot more, but it just makes your system much more difficult to design. And both of these different approaches have been tried. And iterative code refinement is kind of where we are now, where we can go to most systems where, they're in our IDEs, and we can actually say, hey, generate this function, and say, hey, that's not quite right. Can you improve this? And again, we have outcome reward based RL and process reward RL. I didn't get a feeling for which one's doing better, or one versus the other. I guess guys who are building products have got some internal kind of like secret sauce which they use to decide which one they're going to use. And automated software engineering, which is really just the whole task end to end. You're given a code base, here, do this, do it again. Both types of systems are being developed, total outcome based as well as process reward based. And again, the outcome, it gives a couple of examples of systems that actually use that. And then finally, closed source systems, which are interesting because their RL is more fine-tuned. They really want to do preference to what the developers really want, because quite often we want unit tests, we might want documentation, we want it better formatted, we want it to use industry standards or whatever. And obviously they've got to be very safe in your editing workflow. You don't want to start deleting lines and files. Just align to what developers are expecting in their IDE. So RL is used in all of those to train these closed source systems. So the next one that I'll cover is maths. So maths is kind of the gold standard for reasoning, or at least that's how we kind of like think of it currently. It's because it is symbolic abstract. There has to be logical consistency through all the different arguments. The arguments can be quite long, horizon. And there has to be a certain amount of deductive reasoning, that there was like a reasoning process to go from one step to the next. So this is in some sense the gold standard for it. So we have two broad classes of systems here that are being worked on. One is informal mathematical reasoning, where basically you're kind of like in a conversation with the LLM trying to get to some kind of mathematical proof of something. An interesting Scott Aronson, he's a quantum computing expert. He recently wrote on his blog that he'd proved a theorem in quantum computing using GPT-5. So basically somebody sent him a paper with a new interesting result, and he thought it could be made better. He went to ChatGPT-5 and said, hey, this is the theorem that somebody just sent me. I think it can be made better at this, this particular aspect of it. And GPT-5 went away, thought about it for quite a bit and said, yes, I think you're right. I came back with a suggestion. I had to do it. It was wrong. So he prompted again saying, no, you're wrong about that. It doesn't work because of this. And then they iterated over that, a few more turns. And finally it came up with like a formulation that he was pretty happy with. It had been, obviously it needed him to say, hey, no, that's not right. You got that wrong. And this is why you got that wrong. But it was interesting then. He was quite happy with it. He thought, he might use it more in his work. So again, the overall approach is either outcome-based, end-to-end, or process. So this particular kind of class of solutions is really worked really well on word problems and just symbolic computations. But they're not going for automated theorem proving, because that has to really follow the steps exactly, and you have to follow the axioms to be able to do that. And one of the biggest issues is evaluation difficulty. We just don't have enough informal, really good proofs. Most proofs are formal, so that's how we write textbooks. That's how people kind of write them. They don't write informal proofs. The other approach is kind of formal mathematics, where the LLM or the system is given access to a theorem prover. So every kind of step that it generates, the theorem prover has to kind of say, yes, that is actually correct. So again, process reward, one model. Outcome reward, end-to-end proving of a theorem. And there's a couple of systems mentioned there. Or process base, which actually break down to subtasks. There's a system there which DeepSeek have created in that. And there's other approaches where the LLM generates the reasoning for why something should be true, and another system actually creates the formal proof that that's true. So I thought that was quite interesting. But yeah, there's quite a lot of work going on in this area. GUI agents, because they're fun and interesting. So traditionally we've used RL free methods, because basically you're given like say a web page or a static, and the LLM is trained on how to manipulate that particular kind of static web page or static application. And the problem obviously is the data in there. I mean, because you have to give actual human traces of what the human would have done on that web page or on that application. Now so moving on to RL, but in static environments. So this is where we're using reinforcement learning, but the environment is kind of controlled. So it might be like a particular web page or a particular app screen, and then there's a couple of systems there which are used in that kind of context. But the most interesting one is RL in interactive environments. So this is where the agent actually manipulates the browser or an Android emulator, and and obviously its set of actions is a lot more varied now. And there's a couple of systems there for navigating on web pages or on kind of like an Android simulation environments. So again, I don't have sort of like amazing results in this area, but it was just interesting how people are approaching this kind of problem. The paper does go on to cover systems in vision, embodied agents, multi-agent environments, and others like games, handling tables and databases, time series, QA environments, and social. But again, like the overall paradigm is either outcome-based or is process-based, and the process is split up, and you have to reward it in the middle. Each obviously has got some slight complications, but that's kind of like the overall approach that people are using now. So conclusion, so LLMs traditionally were passive. We gave them a prompt, and then they generated the output. We're now looking at them to be more interactive. They're going to generate actions, which generate responses, and that kind of feeds into that loop in the RL. And the amount of obviously innovation in this area is absolutely enormous. There's many hundreds of systems. And one of the nice things about the paper is it provides GitHub links to the source code for a lot of the systems. So if you did want to kind of check it out, that's very good on that. And finally, resources. So if you're interested in reinforcement learning or want to learn more, the main Bible in this area is the Reinforcement Learning and Introduction by Sutton and Bartow. That's pretty up to date. It covers most, of the algorithms we use at the moment, but not the very latest ones. But it's the details in the latest that are different, not the main philosophy or how they work. Second one, if you're more of a developer and somebody who's more practical and learns by actually building things, is Practical Deep Learning with Python. It's Guibin. It's got like algorithms for implementations for most of the algorithms that are kind of like currently being used, or very simplified versions of them. So they're really good to play with. 2 courses online. One is from Stanford. Obviously, it's going to be kind of academic. It's advanced undergraduate, but it's a fantastic resource. And the web site that goes with it's got like huge number of resources for that. And the other one is DeepMind and UCL. They've done a few iterations of this course. Yeah, the original one with David Silver is actually still very good, but obviously that's a bit out of date. But the latest one is from 2021, and again, it's really excellent. Both of these will get you up to kind of like being like really knowledgeable and up to date in this area. So yeah, that's the paper. I don't know if anybody's got any questions.
Thanks so much, Arshad. Yeah, have we got any questions?
Yeah, go ahead, Arvid.
So a lot of it is, for example, the Sutton Bartow is completely independent of LLMs, right? It's reinforcement learning and what it can do. What if you had to sum it up in one sentence? What makes LLM different for reinforcement learning than not using LLMs?
So we know that LLMs have some limited reasoning capability, right? It's not like, but they produce genuinely interesting ways to do something or to think about something, right? I'm not going to try and overstate the fact that they can genuinely do reasoning. I mean, that's probably not true, but having that kind of knowledge base and having that kind of and they are able to suggest, action that you can take if you want to achieve something, right? So having that kind of really rich kind of set of kind of data and information where you can say to it, hey, I'm trying to solve this problem. Can you suggest how are my approaches? And if I have, and if it was trained on how to use certain tools, where you could say, yeah, try this tool and try that tool. In some sense, you're getting all of that for free, and that's what you're really getting from the LLM. It's because somehow your reinforcement learning is going to need to know what action to take. That needs a lot of knowledge. Obviously, LLMs are going to be great in, for instance, LLMs are not going to be great for automated driving, right? So the reinforcement learning in that is not going to need an LLM. Well, all of a sudden, not an LLM until they get to an astronomical size and have full multimodality. But if you're working in anything which is kind of slightly more kind of descriptive or requires a process of some sort, where you're going to be hey, I want to write this code, but I need you to solve this problem and that problem. An LLM seems like quite a good way, because even today I can go to a system and say, I'm thinking of doing it this particular solution in this way, and this is a function I need. It needs to do this. Can you make some suggestions? Usually the suggestions will be pretty good. And they wouldn't have even been bad a year or two ago, before obviously all this code got into it. So it's really as I said, I don't want to kind of anthropomorphize this by saying intelligence and kind of knowledge in that way, because we don't know exactly how LLMs work. But there's some interesting kind of collection of data there that if you give it some kind of good problem, it does give you interesting things which you should try to solve your problem. And that's what LLMs, that's what reinforcement learning needs. It needs, what actions can I do to try and help solve my problem?
Okay, thank you.
Great. Well, thank you very much, guys. And it was fun to learn this stuff.
Thank you so much. That was amazing. Thanks.
Okay. Bye.
Yeah, we've got a session in 2 weeks from now. I'll present a paper called Revisiting Hierarchical Text Classification, Inference and Metrics. So hope you can join us then as well. Thanks a lot.
Okay. Bye.